is going to be on power functions, logistic functions, and data fitting. So a power function is a kind of function that we have not yet studied. We're not going to go into depth at all on all of its characteristics and properties, but it is an important kind of function that can be very useful. And it's a function whose output is directly proportional to some power of the input. So in other words, if I was going to write it in mathematical terms, it's k times x to the p. X is the input, and it's just x to some power. And the thing that makes this different from like x cubed or x to the fourth, a polynomial, is that p does not have to be an integer. Okay? It could be positive, it could be negative, it could be a fraction. So for example, a of r equals pi r squared is a power function. Pi is the k and 2 is the p. Okay. A constant function is a power function because it could be written as, say, f of x equals 2. You could write it as 2 times x to the 0. And 2 square root x is a power function because you could write it as 2x to the 1/2. So it's just a number times x to another number, and there's no restrictions on what the numbers can be. 1 over 3x is an example of a power function because you could write 1 over 3 times 1 over x, which is 1/3 times x to the negative 1. So that's actually a power function. So the most important thing that tells you what the graph will look like is the p-value, the exponent on x. So we have several different cases. I'm just going to show you what they are. It's not super important that you memorize these. I'll give you a little cheat sheet at the end. Okay. So if p is 1, then you just get the line y equals x, right? It would just be x to the first. And if p is 0, you would get x to the 0, which is 1. So those are my first two easy cases, when p is 0 and when p is 1. Now, if p is bigger than 1, you get graphs that look like this. They're increasing and bending upwards. So they look kind of like x squared or x cubed or x to the fourth, stuff like that. And when p is between 0 and 1, like a fraction, they look like the square root function. They look like the square root of x or the cube root of x, stuff like that. They're increasing, but they're bending downwards. And when p what did I just do? 0 to 1. These are root functions. They look the same as the 0 to 1. And then these are 3 power functions where p is negative. So these are decreasing and bending up. So why use a power function? So some data cannot be modeled well by a polynomial. So when we've done data fitting before, we've always done either linear, quadratic, cubic, or quartic, and those are sort of the only possibilities we have. There is an exponential regression on your calculator, so if something looks like it's exponential, you could use that. So if you go to stat, calculate, so you see we have linear, quadratic, cubic, quartic, and then there's ln, which we haven't used, exponential regression, which, have we done that? No, exponential regression, and power regression. So that's one that we haven't used, and logistic. So power and logistic is what we're going to talk about today. So in this example, we have some data where we have planets, and we measured their distance from the sun and the period required for orbit, the length of time it takes to orbit the sun. Okay, so if I get a scatter plot of these data, what polynomial might you use to model this? What would you choose to model this based on your experience so far? Quadratic, yeah, because it definitely looks like it's increasing and bending upwards a little bit, so a line wouldn't be a perfect fit, so maybe you'd do a quadratic. So let's see what happens if we do a linear or a quadratic. We'll do both. So to remind you how to enter data, you go Stat, choose Edit, clear your lists, and we enter the X data in L1, so we have 0.387, 0.723, 1, 1.52, 5.2, and 9.54. And then we put the Y data in list 2. Okay, so if I want to look at a scatter plot, just go to Y equals, clear anything that's in there, highlight plot 1 so that it'll graph your data. And then you just hit zoom 9. That chooses a perfect window for data, zoom 9. So now to do a regression, go to the home screen and you do stat, calc, and we could choose linreg or quadreg. So if I choose quadreg, then I would say we'll use list 1 and list 2 and put the answer in Y1. And I have an R squared value of 0.9998, which is really good. It's a really good fit. Graph it. Looks really good. It's not perfect. 0.9998 is still not 1, but it's really good. And the line would be a little bit worse. The linear regression is even a little bit worse. All right, so roughly speaking, the linear function is going to increase too slow, and the quadratic function too quickly. So you can see that the quadratic was a little too fast. It jumped over this point right here. So let's see what happens if we have the calculator do power regression. Do exactly what we just did. This time I'm going to choose power reg. So I go stat, calculate, option A is power regression. And we do list 1, list 2, put the result in Y1, and we get 0.999997, which is better than the quadratic. And I graph it, looks pretty perfect. And my equation was 1 times 1.5, sorry, 1 times x to the 1.5. So 1x to the 1.5, or just x to the 3 halves. And that relationship was originally discovered by Kepler, but he had to work harder to discover that than we did because he didn't have a graphing calculator. So here it is superimposed on the graph, looks pretty good. So that is just another function in your basket of functions that you can use when you're trying to model data. Okay, so now you have linear, quadratic, cubic, quartic, exponential, and power. And now we have one more called logistic. Logistic functions are often used to model population growth because population growth can't continue to increase forever. So it often increases slowly at first, then speeds up so that it looks exponential. And then once the population reaches some carrying capacity, right, you can only fit so many people before you run out of space and food and resources. So it might look something like this. So the S-shaped curve is the telltale sign of logistic growth, that sort of S-looking thing. So here's some data. We have yeast plant growth over time, and so this is just a population growing over time. It starts out growing relatively slowly down here, then it grows very quickly, and then it levels off as they run out of resources. Okay. So the formula for logistic growth is this guy. Not important that you know it off the top of your head. All we're going to use this for is having the calculator do a regression. So if you have data that gives you this S shape, you should think, oh, that's logistic. I'll do logistic regression. So let's go ahead and do the logistic regression on this data. So go to Stat, Edit, clear our lists. And put in the X and Y data. Okay. So there's my scatter plot. It looks like an S, so I'm going to do a logistic regression. So I go Stat, well, I should go to my home screen here. Stat, Calc, and as I scroll down, option B is logistic. So you do logistic, then you say use list 1 and list 2, and put the result in Y1. And the logistic regression takes a longer time than all the other ones. Has to think for a while. All right, so there we go. It gives you the formula and the values of A, B, and C. So when I write it out, I should get this. So 661.8 is the C value, that goes on top. And then 1 plus AE to the negative BX. And the A is 74.46, and B was 0.552. So that should be pasted right into Y equals, and when I graph it, I get a nice match. So this is just a reminder how to do regression. So you can read through that if you forget how to do any of the steps. And some words to live by when you're doing data fitting or modeling. The more data, the better. If there's a theory-based reason to use a certain kind of function, i.e. quadratics for projectile motion, use that. Use the simplest model possible. So if you can use a quadratic instead of a quartic, do it. And generally using models to interpolate, which means to find values between the values that you know, is more accurate than using them to extrapolate, which means finding values outside of the data set. Okay. So deciding on a type of function, what kind of regression are you going to do? You look at the shape of the graph and narrow it down. Okay, so you get the S curve, you know immediately what kind of function you're going to use. Okay, if you get if you get something that looks like, say, this, you might try a quadratic or a power, right? So narrow down the kind of function you're going to choose based on the shape of the graph. And then you might have to try a couple and see which one gives you the best r squared value. The r squared closest to 1 is going to be the best model. But sometimes it's better to choose a simple model that has a slightly lower r squared value, because we like simple. Generally use the simplest model that fits reasonably well. So these are just some pictures to help you decide what kind of model to choose. And we have general shapes of the various different kinds of functions: linear, quadratic, cubic, quartic, power, exponential, logarithmic, and logistic. So now I'm going to have you work in your groups doing some data fitting. So get a scatter plot, decide what kind of function it has the general shape of, and then do that regression on it.